Hello, my name is Aaron Mazzeo, and I am going to have the opportunity to present convective flow over heated wire simulations in Ansys 2023 R2. This work builds heavily on that of Rahman Pejman and Jonathan Singer. Let's go ahead and get Workbench started. And while Workbench is loading, we can take a look at the geometry we're going to be simulating. We have a span of 200 millimeters with a height of 30 millimeters, where we have an inlet on the left and an outlet on the right. There is a heated wire in the middle. The core of the wire is not meshed, but we're going to specify a Dirichlet boundary condition of 400K on this surface. As the air flows past that surface, it is going to have a no-slip boundary condition around it, and it's also going to get the heat up. We're going to study laminar and turbulent models and see how much of a difference there may or may not be in those circumstances. And we'll also study a natural convection based model. This simulation is not the most rigorous in nature. We're not necessarily looking to show that we have a sufficiently fine mesh or we've taken the perfect model, if there's such a thing, to show that we have high accuracy, but this video will show us how to go about performing these different type of simulations and allowing for future exploration of verifying accuracy and convergence. Workbench is, I'm sure, open by now, and we are going to start by bringing in geometry. So we come down here, we bring in our geometry, and left click on the geometry and change it to 2D. Now we're going to come up here to fluid flow in Fluent, and if we do create standalone system like this, we brought it over here, the geometries are not connected. We can connect them by holding down here and bringing it over, and then we have a link between them. Another way to do it is to go ahead and bring in the Fluent model and hover it over. I have my left mouse button held and hover over the geometry and then drop, and then it automatically does that. Now that we've got our opportunity to model our geometry, I come over here, I right click, and I do new space claim geometry. One of the things about these connectors and having these separate models is the opportunity to take a geometry and run it into different types of physical simulations. So maybe you want to do a mechanics simulation instead of a fluent or fluid flow or heat transfer simulation. Now space claim is open, and we are going to click on this Z right here, which brings us to the XY plane. We select that plane for doing a sketch. Clicking here in the middle is not a bad idea, and we click a rectangle. We then bring it over here, and before I click the mouse button again, no hands, I go ahead and I say, oh, it's 200 millimeters across, and I hit tab, and it's going to extend it, and tab brings me to the vertical dimension. Now I want that to be 30. Now I hit enter, and that is the outer geometry that we desire. We will go ahead and add that semicircular core region. I clicked on circle. Now we see there's a midpoint option appearing here. Bring this out like this. The diameter we want is 25 millimeters, which corresponds to the 12.5 millimeter radius. So just 25 there. And we can click T, or we can click on trim away, either way, but if I click T, it selects that tool automatically, and I trim that away, and that geometry looks pretty good. Come over here, hit select, hold down the left button, select here, then come up here and hit fill, and we've now created the surface. that we can use for our simulation. I do not advise hitting the end sketch editing. Just come over here and click close, and Workbench will update with this geometry. There is not an update button. We see the check mark here, and we know that we can proceed in confidence. We double click on mesh, which brings us into another interface, which will allow us to specify edges where we're going to have boundary conditions, and also, or so we'll name those edges, I guess I should say, and also create a mesh and refine that mesh. One of the things that we discussed when we were doing the meshing or increasing the number of nodes in finite difference and finite element methods was that we could simply increase the number of nodes along the sides when we were dealing with the square geometry, and that would increase the number of elements or the nodes that we have inside. When we start having more regular geometries, the number of nodes and elements and how we refine and have sufficient number of elements and nodes becomes a little bit more arbitrary and a little bit more artistic, quite frankly. Well, we have brought in our geometry, and it's good that we see that we only have one surface, which we can select here. Not necessary to select it, but I did. And we're going to go ahead and name some edges. So I selected the edge select tool here, and we'll do the top one. And this is going to end up being a mirror boundary condition. So we're going to have a no shear. So we're not going to use no slip. Okay, no slip means that there can be shear there. We're going to use a no shear boundary condition. And so what that means is it's kind of like, oh, there's still just other material above us, and we have kind of a symmetry right there, and so we don't expect to see any slowdown of the liquid on the top. We're going to do that on the top and the bottom. So it's like we're extending our region up and down. Here, click on it. I can hit N for name selection, and that's going to be top. We'll call it mirror, like that. For the bottom, I'm going to do this one, hold down control, this one, and then I hit N, and we're going to type bottom mirror. Okay. Now, that's not actually specifying the boundary condition, it's just naming the selection or the edge, which will then receive a boundary condition later. Here in the middle, I click, I'm going to say name selection. We're going to call this the wire edge. Okay, that's the heated region. That's going to be at 400K, and it will have a no slip boundary condition in the future. Over here, left click, hit N. This is going to be our inlet. And over here, left click, then hit N. This is going to be our outlet. These should be stored here now. Okay, so top mirror, bottom mirror, wire edge, inlet, and outlet. Wonderful. Now let's go to mesh. If we generate the default mesh, we see that, well, it does have a mesh, but not exactly capturing or has the ability to capture what we think some of the interesting physical behavior might be. We understand that a lot of what happens in a simulation with finite volume is based on the number of nodes, right? We have, say, temperature or fluid velocities that we find at the nodes or at the centroids of the cells. So the more elements, the more nodes that we have, the higher resolution we're going to enable with our simulation. So we have a rough idea that this is probably not the ideal mesh. What we're going to do is similar to what we did in our last example, where we added elements along the surface or along an edge where we thought there would be some boundary layer effects. So over here and here and here, there's going to be no shear, so it's not as critical. But around this semicircle here, we're going to have a no slip condition, and we would like to kind of be able to capture what's happening physically in a boundary layer. So let's go ahead and add an inflation there. So we do insert and we come down to inflation. The scope geometry is the face. But I still got to apply it there, so that's the face. And then the boundary itself, we are going to come over here, and oh, I had to select first. Oh, that's okay. Select the edge, and then I click apply, and so that's where a lot of the inflation we want to have happen is going to occur. And we're going to up it to 5. Last time I think we used 3. We're going to use 5, and we're going to go ahead and generate. Then we click on mesh again, and notice we now have these 5 much smaller layers here around the wire. Another thing we can do is increase. You see there's like one point here, I can zoom in. There's, one node here, one node here, one node here, one node here. And, actually you can even see that we lose some of the fidelity of the geometry. Okay, right? This is a curve, but these are lines. And also maybe there are interesting effects happening at intermediate locations along these lines. So to both capture the curvature and capture more of the physical phenomena that might be occurring, let's increase the number of nodes that we have around this semicircle. To do that, we go and insert something called sizing. And for this, we're going to, so our geometry scope, okay, in this case, is going to be that selection, right? And we see, oh, it's got it right there. And we're going to decrease that element size down to 1 millimeter. So just like that. And if we generate now, we see that we've captured, remember it was a little bit straight edgy, I guess for lack of a better word, discrete, and oh, I just lost. There we go. What we have here now is a little bit better capture of the geometry, and also we have more nodes here. Now, if we zoom out a little bit, we see that, well, the sizing has helped us here, and so has the inflation, but maybe we want to have a little more density still out in these regions up around. Okay, so to do that, we can go and decrease the growth rate. So this is the growth rate. This is still under edge sizing, and we're going to allow this growth rate to go down a little bit, like we have there, and we hope that that will still capture a little bit more of the behavior surrounding. So we do generate, and we click on mesh, and yes, we see now, okay, there are more elements surrounding here. Now, how many elements do we have? Well, if we go to mesh and we click on statistics, right, we can say, oh, okay, we have 802 nodes and 734 nodes, or 734 elements. And, I might sometimes, if that's interesting to me, I can copy and paste this and just go into my PowerPoint or Word document and just say, okay, look, for the meshing, when we had, we did inflation and sizing, we got to this number of nodes and elements. And maybe that's sufficient for our nodes. Nonetheless, we come out a little bit further and we think, well, okay, so if the inlet's on the left, nothing really interesting is happening until I get to this region. So this might be sufficient. But after I hit this region, we saw backflow over a step. We see different effects that we might want to have a little more density over in this region. Okay, and so there are different ways we could do that. We could do the sizing here, various things, but another technique for refining a mesh is to change the type of elements that are being used in the mesh. So we see here that we have a lot of quadrilateral elements. All right, see here, but that's a triangular one. Okay, that's a triangular one, but they're mostly quadrilateral. If we change the shape size of the mesh, that can also allow us to interact with a number of nodes or number of elements that we might have. So if we click on method, this gives us an opportunity. So we got to do another geometry. So we're gonna select that whole thing and we hit apply. So we got the body here. And right now the method says it's using quadrilateral dominant, which kind of makes sense, right? If I click on this, like we had it, right, you saw that most of them were, in fact, quadrilaterals. Now, though, we're going to change it to use triangles. And when we do that, we generate the mesh, and then we click on the mesh. And wow, we see many more elements here, and we see more elements here, okay? And we see more nodes. And statistically, we can capture that information, 828, and copy and paste it into our file. So after we use the triangular shapes, or triangular elements, we actually didn't see that excuse me, a significant change in the number of nodes. You know, there are more nodes, but we have more elements. Okay, and so hopefully we'll have higher ability or increased ability to capture physical phenomena. When we run our simulations and we think about convergence, we have an opportunity to, you know, before we thought a lot about convergence in terms of the widths of the steps we were taking in both space and time. And when it came to finite difference, you know, we did that. We were looking at that length of nodes, right? And as you decrease the length of the nodes, then you increase the number of nodes that you're going to have. So sometimes what you'll see is that people will plot whatever interesting quantity they might have versus the number of elements, and then, you know, as they've increased it to a certain number of elements and they see that the value is not changing, they'll say that they've got convergence. Well, we're pretty much done with the mesh here. Let's go ahead and update the workbench, and this is very nice to see that that translation was successful. We close and we then come back to workbench and we get to set up Fluent. So this comes up as 2D, nothing really to change here. We're going to go ahead and start. And this is the opportunity to think about the boundary conditions, think about inlet, think about material properties, and look at the temperature, look at the fluid flow, the velocities. This is where the physics are going to occur. And this is a coupled physics problem. Navier-Stokes doesn't have temperature in it by itself. And heat transfer, or the heat equation, right, doesn't have velocity necessarily in it, right? So we have coupled physics here. With the coupled physics, we have an opportunity to turn on the energy, okay? That energy is going to be what allows us to simulate both changes in temperature along with the fluid flow. We're going to be running initially in steady state and planar. Okay, so this is the general tab. Okay, so we've turned on the energy. Maybe that was a little bit out of order. And that's all we have to do with the models at this point. Oh, no, it's not. We're going to first use laminar. Okay, so we're going to edit this and we're just going to use laminar. Okay, like that. Then we can close that. for here, we're going to use air. We don't really need to change it at all at this point. We will change it later, but for now, I can leave it like that. And let's move down to boundary conditions. For the inlet, let's go ahead and put in the inlet velocity of 0.1 meters per second. And we hit apply, then close. It's good to hit apply. For our outlet, we don't really need to do anything. For our walls, yes. So we said this is going to be we're going to have a couple of mirrors. So I'm going to click here. Whoops, not like that. Click and then shift. So I got them both, and then right click and then do multi-edit. And so now we can specify these boundary conditions at the same time. We're going to not use the no slip condition, so that's double negative, I guess. So it means like we're kind of slipping. And we're going to say that, yeah, there's going to be shear stress with this slipping condition. And it's going to be 0 or no shear stress, okay? Sorry, that was a little confusing the way I said it. And then thermal, we're going to specify nothing at this point. We're just going to leave it as 0, okay? These are the mirrors, all right? So, you know, you could do something like with temperature or flux, but we're just leaving it as nothingness, okay? So momentum, we hit apply. Okay, that check mark, those check marks are gone, and we hit close. The wire, okay, so that's this region in the middle. It's going to be a little bit different. So let's go ahead and I'm right-clicking and clicking edit. I could just double-click. That's fine. Here we are going to have the no slip condition. So if you look at this problem from the side, what you're going to essentially see is no slip here, and I've got these mirror on the top and the bottom. So if you think about that bottom, I would look from the side and I'd actually be able to kind of see the flip problem, okay, where I would have not just a semicircle, but I have a complete circle, and I've got symmetry in 2D. So, you know, the fluid flow above is going to be what the fluid flow below would be as well. So we have no slip here, because that's an actual, that would be like a cylinder. So imagine having a long cylindrical wire going in and out of the page. And it's going to have temperature there. So we're going to say that's 400 for now. Please note that your assignment will involve changing this temperature. So I apply, or your lab assignment right now, what you're going to turn in a few minutes, we'll have that changed. And we can move on down. Something that is very cool here is that we can, so I'm now in the report, we can do a flux report and we can have it tell us the total heat transfer rate from the wire, okay, to the rest of the system. This is really neat, okay, and I'm surprised at how simple it is to do in Fluent compared to some other software packages. So hit OK. All right, there's nothing, it's not telling us anything right now, but it will tell us, and I guess I can rename it. This will be the, actually maybe I have to rename it over here, yeah. So this will be the wire heat transfer. Okay, great, we'll say. Okay, that's pretty neat. Okay, and so that's a cool thing. That's going to be just around that border. And then when we come over here, oops, not there, double click on Run Calculation. We're going to go ahead and let it do its thing in terms of automatic time method, but we will have it do 1,000 iterations. And we will go ahead and let this thing run. So initialize and calculate. So this is laminar, and while it's running, okay, I'm going to just create another PowerPoint slide here. I'll call this laminar. And this was at 0.1 meter per second. And what do we have? It's still running. Okay, the residuals they've kind of bottomed out. And notice that the residuals under monitors, oops, okay, I guess I can't get access to them right now because it's running. But the console has automatic thresholds. And I just like to point out that we've hit them for x velocity, y velocity, and energy, but we actually haven't hit it for continuity. And it was down like at 0.000 or 1 e to the minus 3, and we're only getting down to 1 e to the minus 2. Okay. That may not be super important for what we're doing right now. Again, we're just trying to show that we can run these simulations under different conditions, and how you can go about doing that. And then when you want to look at convergence, or is this solution accurate or good enough, you might want to go further in terms of refining the mesh, increasing the number of iterations, changing the model, right? We're starting with laminar, and let's see, does it make a big difference if it's laminar or turbulent? Okay. So our calculation is now complete. It's kind of fun, even before we do anything else, we can look at what the heat transfer coefficient is. So it didn't really change after all these iterations, right? We're doing steady state, but essentially it's about, if you can see that, it's about 30.95, so like 31. So I'm just going to take a screenshot here, and I think that's kind of cool. I guess I don't know, can do it like that. Okay, so that we'll put over here, and kind of, again, I think PowerPoint or Word or whatever you like, but taking screenshots with a few parameters, I forget my parameters, and so I think it's nice to be able to record them. All right, and so for contours, let's go ahead and let's do a new one for temperature. And we'll call this a temperature contour. Like that. And we'll do save display. Okay. And yeah, that's kind of cool, right? Kind of makes sense. Fluid's coming from the left, and then it hits this hot wire, and then you see that as the fluid continues to flow, it has a higher temperature. So that makes sense, right? That's reasonable. We can maybe want to capture this information as well. I'm going to make this a little bit bigger like that. And I'm just going to do a screenshot. That's not the best screenshot. Here we go. Okay. And bring it into PowerPoint. So things are making sense, shall we say. I'm going to drop this down. I just made the maximum width. Maybe I'll make this a little bit smaller. And the actual thing that's kind of interesting is it's 31. Oh, and I guess I should tell you what the units are. Ooh, I didn't tell you. So if you go back into Workbench, this is a power unit. So if I come over here, double click, and actually if you hit compute, it will tell you what it is right down here. So it's in watts. The heat transfer rate on the wire edge is 30.95 watts. Okay, that's neat. Okay, and then back to the contours, maybe we want to do velocity contours as well. So we hit velocity, and we'll say this is going to be velocity contour like that. And we do save display, close, and what do we see? Do things make sense? Well, we said that the top is a mirror boundary condition, and as the cross-sectional area decreases, we see that there's an increase in speed. That makes sense. And as we go over here, there is a decrease in speed. Okay, over the hump, kind of like the back step that we had in the last simulation. And we see that there's really no effect of these edges, right? We don't see a gradient in the velocity, and that's good. That's what we wanted. We do see, once we have the no slip condition engaged around this heated wire, that you do see a change in the velocity and the gradient there. Okay, so we'll capture this, and bring it into PowerPoint just so we have, and I'm going to even do a duplicate slide, right? And then I'm going to replace these two plots with the Control V with the one I just took. Okay, and I think there's one more plot that we might want to capture, which is a vector plot. So if we do new here, we can go ahead and have velocity plotted, and we do save display, and we get, it's pretty neat, right? We see, even though this is laminar, okay, we can see that the model is capturing, okay, some backflow and some circulation, and it's capturing an increase in speed across the top, and it's capturing some slowdown, right, as we encounter this no slip condition here. Okay, so this is kind of a nice plot too, and maybe I'm more interested in what's happening here as I've gone over. Okay, so I can go ahead and I can do a screenshot there. Okay, these are not report quality captures, okay, but it's kind of for our remembrance and for our documentation of what is happening here. Okay, and that's good. Let's go ahead and change the model now. And to do that, we go back into Fluent, and what do we? Oh, I guess maybe I'll go back to the PowerPoint and say, what do you mean by change the model? What are we changing? Well, we have an opportunity to change speeds, and we have an opportunity to use a turbulent model. And then we have an opportunity to move to a transient model, which is using natural convection. Okay, with gravity, we have not specified gravity here. So let's first do turbulent. We come up to the models, and right now we're doing laminar. We do a model, and we move down to standard K omega. K omega, we'll talk more about turbulent models in the class, but K omega is one that can help us capture interesting turbulent behavior near boundaries. Okay, so all we've done is change that model, and we can come over to run calculation, and we do initialize and calculate. Okay, and we're going to proceed, and we're going to let it run like this. And while it's running, I'm going to come into PowerPoint and just prepare a little place for turbulent. Oops. Okay, that was fast. That was fast. It ran it. That was faster than laminar, right? So turbulent. And this is still at 0.1 meter per second. Okay, just like that. Come over to Fluent, and what do we see? Well, we got, okay, we could have, right, we had more iterations possible, but it's saying that it was good enough. It converged according to its standards here in about 80 iterations. What does the temperature profile look like? What does the velocity profile look like? What does the heat transfer look like? So let's look at a report. So first, all right, we see that our new heat transfer rate is 30.93. So very similar. So I'm just going to take a screenshot of that. Actually, it didn't, that was the wrong sequence. Now I'm going to take a screenshot of this and capture what the heat transfer rate is there. And you know, the simulation ran more quickly. It was using turbulent, and so that may be an indicator that, you know, we should have had turbulence involved earlier. And we have this circulation, so that's another indicator that, you know, maybe turbulence is adding using a K omega is more representative of what's actually happening. But as you'll see, the actual simulation, the differences in the outcomes may not be so significant. So, you know, it took 980 iterations, or 1,000 iterations, right, to get us at 30.95, and now we're at 30.94. Okay, not a huge difference, you know, in terms of watts. Let's look at what velocity and temperature look like. Oops. If I come down to the contours, and let's do velocity contour, right click, and let's display. Okay, so it's a little bit zoomed in, I guess. But this is velocity. We'll copy and paste this in to our PowerPoint. And we're modeling turbulence, and we see some separation. Come on, I don't need that anymore. There you go. Okay, and we see things, but if we look at what's happening here with velocity compared to what we saw here, we see a little bit of this, like kind of interesting slowdown, and this is kind of dead, and in the vector plot we see that, but we kind of see it too, and it's hard to argue that this is a much more higher fidelity simulation than what we have here. Okay, it looks pretty similar. We can go ahead and, or maybe I'll do a duplicate. I'll Control C this, Control V this, and I'll just record the temperatures, display, and yeah, this might be a little bit more, and again, if you have an analytical solution, or you kind of know what you're looking for, you've done an experiment, right, and you're trying to get higher fidelity, it's like, okay, there's some kind of interesting, here's a little bit more contoured here than it was previously, so this is now here, and this is what we had before, but not really, it looks pretty similar. And the temperatures are not that different, okay? So, laminar may not have been that bad a choice. Let's go ahead and run, but the simulation did run faster, right? With the k omega. Let's change the inlet velocity for this system down to 0.1 or 0.01 meters per second. Now, let's ask ourselves a hypothesis, or let's ask ourselves a question and make a hypothesis. We hypothesize that the heat transfer rate will be dependent on the inlet velocity, so the flow over the heated wire. That's a hypothesis. We might even hypothesize further whether it goes up or down. What do you think? Do you think that the heat transfer rate will go up as I slow the flow over it, or will it go down? Well, let's find out. If we run the simulation again, we right-click, initialize, and calculate. We'll go ahead and do that. And we're running a slower velocity, and it got us to a result pretty quickly. Let's look at what's happening with temperature first, okay? Because this may be counterintuitive to our hypothesis, but then I think our hypothesis was not bad, and it was pretty thought out, so that's okay and fun. But keep thinking about it, right? What happens to the heat transfer rate? So here, okay, we had slower inlet coming to the left, right? And so now, if the fluid is flowing more slowly, that has a chance to heat up more of that fluid, and so that fluid that comes over, it is going to be hotter. So, and that makes sense, right? You have a higher residence time for that liquid, right? It's spending more time in nice proximity to the heated wire. So the temperature here, right, as opposed to, say, this simulation right here, right, it was not, the red didn't go as far out, okay? It goes out further here, okay? So you're like, okay, so now wait, what does that mean about heat transfer rate? Well, you could have increased local temperature. It's been residing there longer, but does that mean that the heat transfer rate went up? Well, let's find out. And we go over to there, and we put our little mousey over here, and we take a screenshot, and maybe you can see it, maybe you can't, but that says 11.4 watts. Okay, 11.4 watts. That's lower. Okay, this is neat. This is neat. 11.4 watts. So we ran more slowly, okay, and we had a lower heat transfer rate. This makes sense. If our goal is to heat, a plate or something, and I have hot air, and I have it at some temperature, right? I want to blow as much hot air on that surface as I can to get it to heat up more quickly, right? And it's like a blow dryer, right? Do I use a low setting or use a high setting? So if I'm trying to get a lot of heat flux, I'm going to use the high. If I want to use the high velocity, if I can get that temperature of the air to be more or less the same, whether it's and even if it isn't, just having more flow, right? I'm able to kind of expose a given area of material or solid, for example, to more more air at a higher temperature, and that's going to lead to a higher heat transfer rate. So this is typical that we see that the heat transfer rate is going to, other things, being the same, like the Dirichlet boundary condition for temperature, we're going to see a higher heat transfer rate. But the air itself spends less time right there, and so it's not going to necessarily heat up as much or cool down as much locally, but it's spending more time there. It would be better if it was like, a higher temperature differential essentially for higher heat transfer rate. So that's pretty neat, okay? That we can run this kind of calculation. Right? And this is like, now we're talking truly coupled physics, where instead of having to use some type of correlation or some type of H, we're able to run our air, run our boundary condition for that temperature, and we can figure out the heat transfer coefficient. Okay. Now let's go ahead and embark on the final type of convection that we want to model, and that is using natural convection. So for that, we're going to do that with a transient model, 10 seconds. Okay, so if we come over here and we go to General, double click on General, we are going to switch to transient, and we're going to add gravity. And in this case, we're going to say it's minus 9.81, or 9.8, it's fine, whatever. Okay, and so that will give us gravity, okay, in the minus x direction. And we're going to then change the fluid, the air, okay. And we kind of skimmed over this last time. I don't think we opened the air material. But here, we're also going to say that the density can change with temperature. Okay? And that's like, a radiator that has air surrounding it, right? But then it ends up being able to create a circulation because it heats up the air. That heated, less dense air is able to rise, and it cools down, right? Because it's transferring heat into the room, cools down, comes out to the bottom, and then you can get these circulating patterns. So for that, we're going to use ideal gas for the density, and we're going to do change or create, and we're going to close. And yes, it's like saying, okay, maybe we want to do something a little bit differently when we define that. So we have our gravity, and we have our ideal gas. We're still using energy. Let's go to the inlet, and let's specify that to be 0. Okay, so now we're saying that we're not prescribing a flow into the system at the inlet. Apply, close. Okay, and we're going to go into our run calculation properties, and we say we're going to run for 10 seconds. So we do 10 1 second time steps, and we can up this to 100, and we can go ahead and we can initialize and calculate. Okay. So now we let our system run, and we're saying that it's essentially buoyancy that is going to dictate the flow of air, and that buoyancy is coming because we're saying the density can change of the air, and we have introduced gravity. So this is running for a little bit. 60, the residuals. Okay, so we're running 10 seconds, 100 iterations, okay, for every second, essentially, is what we've got. That's the max number of iterations per time step, and we're hitting it. So, maybe we would want to change things for another simulation so we don't just get to our maximum every time. All right, and let's take a look. So around here, let's maybe velocity. Let's look at the velocity contours first. So display the velocity contours. All right. So here, and let's do a vector. Okay, so we can see which way the fluid is really flowing. Okay, so fluid is coming, and it's you have these interesting circulation patterns. Okay, so let's see. You could have air, here coming around, hitting it, okay, and it's coming up and around, and it's circulating over here. Okay, there's kind of a flow of air above, right, coming this way, and a flow of air below going the opposite direction. And you see these circulation patterns, right? So we said that both gravity and buoyancy would be playing an effect here with the change of temperature. So this is pretty neat looking. All right, and we do have some kind of flow happening this way, more or less, right? Because you see like more of the liquid or more of the air is coming in this way, and then temperature, and then we have some kind of velocity that's higher here, and maybe that's more indicative by the temperature profile. So we see that, okay, we've got some liquid circulating here, or some air circulating here, and so we've got higher temperature in this region. Okay, so these are neat plots, all right, and we can take a snapshot of this. Okay. And there are similarities in terms of the temperature, of course, being highest near the wire, okay, which is what we see there. And this vector one I think is kind of neat too, right? And we can see the circulation happening like that, and we can see these directions. Okay, it's not one direction like the band, but it's kind of beautiful. All right, and so I'm just keeping those in there. I'm also interested in, let's see, natural convection. Also interested in what's happening with the heat transfer coefficient. So if we go back here, or not heat transfer coefficient, just what's the heat transfer rate? So if I come over here and we do a compute, okay, it tells us, oh look, that heat transfer, it's up at 30.5. Okay, 30.5. So where was that? That's scaled residual report. Yeah, it went up. All right, so as we let this simulation go, right, it did go up. So even though we had no velocity specified on the left side, there's still that's 30.1. What, this is, maybe I would capture the whole thing here, because this is the calculated heat transfer at the end. And you could argue that we haven't necessarily run this long enough to fully develop, because there's still some slope. I mean, it's more or less flattened off, but this is a pretty cool result too. Okay, that for these conditions the heat transfer rate is comparable. Okay, where is this? Oh, that's because it looks like the simulation. That's why I'm confused. It's like, oh, that's another simulation window. Okay, just like that. All right. So I think this is pretty neat that Ansys Fluent is able to tell us the total heat transfer rate, and we're able to see how the fluids flow under natural convection as the gas changes density. We're able to make comparisons between the turbulent model and a laminar flow model, and we essentially just went with the turbulent model. And we also have kind of seen how we can go about organizing and making meshes and how we can refine them. And I hope that this exercise is interesting and helpful as you're planning your final projects for the course. Thank you.